We will sit in the back or we will stop. R square should not be negative. So for building the model from sklearn dot linear underscore model linear regression, reg is equal to linear regression, reg model is equal to reg dot fit x comma y, reg model dot score x comma y, 88.75, which is a good R square, right? Which is a very, very good R square within the range 0.60 to 0.95. What is R square? The amount of variance occurring in the dependent variable explained by this model. That means 88.75% change that is happening in the dependent variable sale price is explained by this model, which we have built, linear regression model. Now, this is a competition data set, so we need to predict, right? So reg test spread is equal to reg model dot predict test df. Oh, we didn't drop ID column from house test. That is why it is came from. House test df is equal to house test df dot drop comma axis is equal to 1. The ID column we dropped from train data, right? We forgot to drop it from here. That's why we didn't get the error. Now pd dot data frame dot to underscore CSV reg dot write it into a CSV file so that we can copy paste the predictions to the sample submission file and submit. If we have done it, copy paste the predictions to sample submission file and upload in the competition. And tell me what is your score. Go to the folder, project folder, you will see the file reg.csv. Yes. What column name? There should not be anything. Under sale price, you have to put that data. You should not add columns or delete columns. So, the values only, not the header. So, if you go to, if I go to where is hackathon? Yeah, house price prediction, open with Excel. The reg CSV is also open with Excel. So, all of you can watch. See, this is the predicted values which are coming in logarithmic. We got logarithmic values, right? Because we have converted it into log p 1p yesterday. Yeah. So we got the logarithmic values. Control shift down arrow, come under sale price. Do not touch the first column. Do not touch the headers. Control V, Control S. Okay. Control V, Control S. Don't touch the ID column. Don't touch the sale price. Below sale price, second row onwards, you paste it and save the file. Okay. Then once you save the file, go to the competition site. So submit predictions. Click on submit predictions, drag or upload the file, click on browse file, hackathon price prediction, sample submission, open. Enter a description and submit. So it is scoring the submission 9.45907. Oh, actually, okay, we have to convert and submit. We have to convert and submit because the score is not coming correctly. So pd dot data frame np dot exp1 exp1p exp1 np dot exp. Opposite of logarithm is exponential. Let me check once. Open with Excel. Yeah, now we got the actual values, right? And sample submission. Earlier it used to take log values also, but I don't know why they changed the format. Copy the values, Control C, paste it in sale price, Control V, Control S. Then maximize house price prediction, browse file, sample submission, click open. See 0.14116, 0.1411. So the leader position would be 1,673. Out of 4,000 people, we are in top 50%. We entered into top 50%. Total is 4,400. Some people are there. So we got into top 50%. Next challenge is to get into top 24%. That means closer to 1,000 to 1,200. Then top 10%. Like that, you have to fine tune your model and come up with the strategies. Right? Base model, base target, we got up to 14116, 1,673 rank. Okay. So all of you got the procedure how to submit. So let me show you the notebook of converting the prediction to exponential. Submit, all of you submit. Getting error or any problem, you call me. Reg dot. All of you getting Got it, all of you? Submitted? Use the file which I sent you or some error which is coming. Okay, all of you submitted? What happened? That is because you didn't do the exponential. Yeah, the exponential చేస్తేనే as per వస్తుంది. np.ext. Yes. Decision tree. People are done. Decision tree regression. Huh? You must be using copy paste this. Huh? Upload the same file. Yeah. You paste write the data into sample submission and then upload. sklearn decision tree regressive. So tree model, we have overfitting, right? 0.9. Okay, no problem. We predict is equal to tree model house test df. We predict what we got. PD dot data frame and p dot exp dot to underscore csv 3 dot csv. So submit predictions, browse files, sample submission, open decision 0.20. 0.20. Yeah, exponential. 0.19 random. Closer to 1. So let us reduce the overfitting by using max depth 9464, right? Let us check cross validation also. Yes, somewhere around 75, max depth 8. Let's see if I can do it with max depth 8. With 8 also. 0.19315, not much of a difference. So this is the process for decision tree. All of you can do the decision tree. Yeah, the rules will be there, no? The rules are used for prediction. No, based on the rules only the prediction is being done in the back end, right? Max depth 6 levels in the tree. How will you know when to use login? How to use login when to use exponential? Data pre-processing on book open. When you have positive skewness, logarithmic transformation. When you have negative skewness, exponential transformation. It's based on dependent variable skewness. So in this case, the dependent variable is skewness. Yes. Enter. There is in this case. Go to the Excel sheet. See, in the test file, there are only 151459, right? The sample submission file. Delete this and download this. what folder you have given. It is suggesting here, right? What is the new folder is given? First, below the one, what it is suggesting? Let's see column numbers, control C, remove the double quotes completely. No, see the double quotes, now change the name of the folder, whatever folder name you have given. Then house only, this house only, that folder is not effective, that folder is not the problem. The problem is somewhere you have done pre-processing, there it got over. 100 Our y is logarithmic only. What is y? Print y. Y dot head. It is logarithmic. See, once you finalize your y and x, they will be same shape. It doesn't change. Permanently, we have given y as a logarithmic value. So whenever you do prediction, it will generate logarithmic value, whatever way with the model. So if you want actual values, you have to convert it using exponential. Small data, na? Why depth is not affecting here is because of the small value, small size of data set. We have only 1450 observations. So in case of so the thing is, this is a small data set. That is why depth is not working in decision tree. Already it is building a smaller depth tree. By reducing it further, it is not able to give any value addition. Suppose you have 10,000 observations, 20,000 observations, or 1 lakh rows, like that if you have, then depth will be a big player. But here it is only 1460 observations, 1460 observations, a small data set. That is why decision tree is not performing that great. But if you are working on large data, you will definitely see decision tree is a better model than linear regression. All right. Can we move forward? Within machine learning, within supervised learning, multi-tree models, also called as ensemble multi-tree models, also called ensemble techniques. In ensemble techniques, one of the important method is bagging. And in bagging, the popular algorithm is random, machine learning, supervised learning, multi-tree models. In decision tree, you will get only one tree as we can define hundreds of trees, thousands of trees based on our requirement. Hundreds, thousands of trees can be built, and these models are called ensemble methods. Multi-tree methods are called as ensemble methods. Within ensemble methods, one of the prominent method is called bagging. Within bagging, the most popular algorithm is random forest. Bagging is a method of ensemble, and a popular algorithm in bagging method is random forest, also called as bootstrap aggregating. Bagging is a sampling method. Bagging is a sampling method, or it's an ensemble learning method, is an ensemble method that helps to improve the performance and accuracy of machine learning algorithms. Particularly, it overcomes the overfitting problem in decision tree. So, random forest algorithm overcomes the overfitting problem, which we see in the decision tree algorithm. One of the biggest disadvantage of decision tree algorithm is random forest algorithm was developed to overcome that problem. It is an ensemble learning technique which improves the performance and accuracy of machine learning algorithms. And particularly, it overcomes the overfitting problem in decision. So you can see here, bagging avoids, it is both a regression and a classification algorithm. Now, what is this bagging or bootstrapping? Is a sampling. It is a sampling technique. Now, you can see from here what that sampling technique will do. So, we have 10 rows of data. Let me just reduce the zoom. We have 10 rows of data. Want to AC reduce or do one thing, you shift to the front row. That way you can avoid it, or you can shift to the back row or front row. Shift to the front row. It will be okay. In front row, it will not come. You have 10 rows. You have 10 rows of data. See here. Sample 1. Sample 1, 2, 3, 6, 8, 4. Sample 2, 6, 9, 2, 1, 10. 5, 7, 2, 6, 8. So you see here, sampling is replacement. That means observations are repeating. Rows are repeating in multiple. Rows are repeating in multiple This process we call it as bootstrapping. So random sampling method. Bootstrapping is a random sampling method with replacement. That means observations which came in previous samples will also repeat in future samples. That is what you can see here. Bootstrapping or bagging is a sampling method. Data is created using with replacement method. This is the core of random forest. The sampling is the core of random forest. Random forest. Random refers to and forest refers to the algorithm random forest. The name of the algorithm is random forest. Random refers to the sampling method. Random sampling, unbiased sampling. You have no control in random sampling. When you are using randomized sampling, it is purely random, no control is there. So it can pick up anything within a particular range. So forest means multiple. Random forest is an iterative multiple steps. The number of trees to be built. In Python, the argument is n underscore estimators is equal to 1000. That means you are asking it to build 1000 decision 1000 decision trees is what? N underscore estimators 1000 means you are asking to build 1000 decision trees. Like how we build a normal single tree, similarly 1000 trees will be built. Now, the step 2 is the most important step, and if step 2 fails, the algorithm will also fail. Step 2 is the most critical part of the algorithm. And if something goes wrong at this step, the algorithm will automatically fail. Now, it has to create 1000 samples of data, and each 65% of randomly or observations square root of. So each data sample will have randomly selected 65% of the rows or observations, randomly selected, and square root of number of variables randomly. Suppose you have 10,000 observations and 16 variables. Suppose you have 10,000 observations and 16 variables. 65% of 10,000 would be 6,500 rows. Square root of 16 will be 4. That means each sample will have 6,500 rows and 4 variables only. Not all variables. Only 4 variables will be there, randomly selected. Again, rows are randomly selected. Columns are also randomly selected. How many columns per sample? Square root of number of variables. Square root of number of variables per sample. 65% of the randomly selected rows. Right. And it has to create like that 1000 samples. If something goes wrong during the sampling process, the algorithm will fail.
Something goes wrong, doesn't include any variable.
No. Suppose your data is already say 2 GB. You are creating 1000 samples of 2 GB data. Will it reduce or will it increase? It may go up to 10 GB. Can your RAM handle 10 GB of data? Will RAM have your 10 GB data? Your RAM is 8 GB RAM, right? And you are giving it 10 GB data. Obviously, the RAM will fail. It will say memory not enough. So particularly, the biggest problem is this algorithm has only one disadvantage, which is the computing problem. It requires large scale computing. Typically in business, it is run on servers because data will be large, right? Forget 2 GB. If you have 500 MB data, you are creating 10,000 samples of data, means it will go up to 5 GB. 5 GB means you have 6 GB RAM. If you are asking it to go with 5 GB memory, it will not go because other tasks will be running. So that is the only problem it has. So the memory problem will come. If data is large, so you will get a memory size error. It says insufficient memory, cannot handle whatever is the 6 GB or 2.8 GB or 4 GB data, it will simply say cannot handle. So that is the problem here. Step 3 will start creating 1000 samples of data. Decision trees parallelly built. Each sample is independent. Since each sample is independent, you can parallelly build multiple trees at single point of one decision tree per sample. So if you say 1000 samples, 1000 decision trees will be built based on your CPU cores. Based on how many cores your CPU has, it will build 4 trees, 6 trees or 8 trees parallelly. Parallelly, build trees will be built depending upon your CPU codes. Parallel building of trees will be done. Prediction will also be for each, prediction is also done for each. All predictions are aggregated. In case of classification, majority voting. In case of regression, averaging is done. So let us say observation 150 came in 400 samples. Observation 150 came in 400 samples. And you are doing classification problem. 220 times it is predicted as yes. 180 times it is predicted as no. So the final prediction will be yes. 220 majority voting. If it is regression, average of all the predictions. Average of all the predictions will be taken in this case of it. So your final prediction will be based on majority voting in classification and averaging in regression. Pre-splitting methods are similar, which is the default method, probability square. Right, is 1 minus sigma probability. The second method is and information, and the third method is variance reduction. This is for regression. The first two methods are for classification. The third method is for regression. Actual decision trees will be built. Actual decision trees, like how we build a single tree. Na? Similarly, same process is followed in random forest also. Same tree based methodology is followed. Splitting is lowest Gini first split, highest information gain is first split. All the processes are exactly same. Feature importance, feature or variable importance is provided part of output. The only disadvantage this algorithm has is computing power. Exactly same tree, but it is multi-tree model. You will build hundreds and thousands of trees. Yes. Tree building is same, but the sampling process is completely different. This algorithm's core strategy is sampling. Bootstrap sampling is the most important part of the random forest. Sampling with replacement. Okay, can take a break and we'll meet after the break. Okay, so there is no fixed formula to decide how many trees to be built. There is no fixed formula to come up with n_, estimators. So for the number of trees to be built, we use grid search models, or in case of R, we have a metric, we have a plot where we can see from which point the error is getting constant, that we can identify in R. In Python, we don't have such plots. So in Python, it's all about trial and error and grid search. Grid search means you can give different tree numbers, 100, 200, 300, 400, and it will build models with all those different number of trees, and it will give you the best fit. So that is what we have to do. So there is no fixed formula to identify how many trees to be built. It all depends on trial. Obviously, lowest RMSE, highest accuracy. We have the metrics now already. High R square and low RMSE for regression. High accuracy and all the metrics should be in 0.70 to 0.95 for classification models. Okay, so that you need to. So the core of random forest is the sampling methodology. Any doubts in random forest? Let us implement this from sklearn.ensemble random forest regression 1000 decision trees on and off. Yes, that's what I told you. Now you have to come up with a random value first and then build a model, then check with another value. In case of R, we have the see for random forest. Generally, what we do is we build the model in R, come up with a number of trees at which the point the error is stagnating, and then we'll take that many trees. But that option we don't have in Python. It takes time. Now, first sampling has to be done, and during sampling, if some problem comes up, it's a problem. It will stop there and fail. Hello. Yes. किया तो था, लेकिन I was traveling, so I could not authenticate it. नहीं जरूरत नहीं. Actually, I think this limit is same for my existing card, right? See, if you take the average, it is far better than decision tree, right? In decision tree, the average was how much? 73 or something like that, right? If you want, you can take the average. np.mean, square bracket to square bracket, you take it, 76.12. whereas the train is 94.20% difference is there. Whereas in this case, train is 98. If you take the average, see 87, 10%. 10% only, 10% is okay. We have to go with some sort, no? We can't get the exact model every time. So 10% is okay. Whereas in case of decision tree, it was 20%, which is a big difference. Train model and the cross-validation models. Here, train model is 98.34. On an average on cross-validation, we are getting 87. 10% only is the difference, plus or minus 10%. So it's a good model. This is how cross-validation is overcome by. What is the biggest disadvantage of decision tree? What is overfitting? On train data, you will get a very high accuracy. When you do a cross-validation or repeated testing, the accuracy drastically falls, right? So here, what is happening on the core train data, you got an accuracy of 94.64. On repeated testing, it came down to 0.76 on an average. That means there is a difference of 19 or somewhere 0.19 or 20 difference is there. Whereas on random forest, the core train model got 98.38. On repeated testing, we got 87, which is less. Only 10% is the difference. 0.10 is the difference. For compared to 0.2 of decision tree difference, this is far better. Random forest overcomes the overfitting problem, which decision tree has. Got it right? The difference between the trained model and cross-validated models in case of decision tree is very, very large. The difference. Here it is very, very small in random forest. Trained model is 98.34. Repeated testing 87.31. Now let us predict. RF predict is equal to RF model dot predict house test here. PD dot data frame np dot exp dot 2 underscore rf dot csv. Submit it. You will come to know what is happening. You will understand the model performance. RF 1000, right? Oh, 14311. 0.14311. Receive it 3000. 315, 311. All right, got it? Okay. Machine learning, supervised learning. Yeah. Ensemble methods. The second type of method is boosting. Boosting method. The popular algorithm is gradient GBM. Gradient boosting machine is a popular algorithm within boosting methods. Boosting algorithms are developed to improve accuracy machine learning models targeting weak learners or wrong. The purpose why boosting algorithms were developed was to increase the accuracy of the models or to reduce the error of the model. They particularly focus or target weak learners. Weak learners means wrong predictions. Those observations which are wrongly predicted, be it a classification model or a regression model, these wrong predictions are given weightage and they will be passed through multiple trees so that they will be correctly predicted at some point of. So boosting algorithms focus exclusively on weak learners or wrong prediction. Gradient boosting algorithm is both classification and regression algorithm. Same thing, step 1, the number of to be built. N underscore estimators is equal to create sample 1, 65% of observations and square root of number of variables randomly build decision tree for sample 1 and predict. Identify and move them to sample 2 and replenish the sample. Decision tree 2, identify wrong predictions and move them to sample 2. Sequential building of trees. It is sequential building of trees as each dependent on previous boosting the wrong predictions. Put this thing down. Oh, she's sitting there. Okay. Put it onto the top straight. No, on the swing. Now, when it goes to the straight, then stop it. Press now. Yeah. Weak learners or wrong predictions are given. Weightage in trees.
Moving the wrong predictions and
Till the number of trees you have specified. 1000 trees, no? So it has to go to 1,000 trees. Should build 1,000 trees.
The weaker model, the weaker.
See, after tree one is built, wrong predictions are identified. They are moved to sample two. And remaining observations will taken from the data universe. Sample two will become along with the wrong predictions and the new observations from the data. Then decision tree two will be built. Prediction will happen. Again, wrong identifications will be there. Move to sample three. This process will go for 1,000 trees. Now, after 1,000 trees, you still have error. You still have the problem.
Can we achieve 100%?
There is nothing called 100% in thing. If it is 100%, it becomes an overfitting problem.
But we are like correcting every now and then. Every time we are correcting.
Yeah, see,
Then
the problem with accuracy is when you get new data. It's not this model you are going to use. You will be using this model on something new data. So every time the data flows into the model, it should have some stability in performance. It will not give you exactly same R square and exactly same accuracy when the new data comes. It should not deviate plus or minus 10%. If it is deviating plus or minus 10% above, then you have to go back and check your model and rework the model. Where the new data is coming, whether the new data is coming with skewness, outliers, or what is the problem, then you have to go and fine tune the constant monitoring process will happen. See, every day new data will flow into the model, and data changes. So when the data change happens, the models will also behave erratically. Now, whether this error is within the limits, you are okay. If it is outside the limits, what company says, each organizations will have plus or minus 5% or plus or minus 10%. If the change is beyond that limit, you have to immediately go to the model. Before going the model, you have to check the new data, check its skewness, outliers, and all those descriptive statistics and all. If you think the data is okay, then you go and check the model. So first we check the new data, do the exploratory data analysis, check how much deviation is happening from the data which we used for model building. If the deviation is very less, that means there is some problem in the model. You will go and fine tune the model according to the new data. So that is the job of the data scientist. Constantly you have to model. So what happens is there will be specific days on which the data will come into your model. So you have to monitor that. So typically what we generally do in real-time data science is before the new data flows, we block it, understand the new data, compare it with the existing data. That is where your Power BI and Tableau will come into picture, data visualization tools. You already have created a data visualization for the tools, for the data which you have built a model upon. The visualizations which you are doing and all EDA and all. You bring the data back into Power BI or Tableau, create those same graphs and see how much the deviation is happening. If the deviation is limited, then you send it, you remove the checkpoint and you send the data to the model. Then you import the metrics of the model and you will check whether if it is all good, you are okay. If there is some change, then you have to go and check the data or you have to check the model. First, you check the data. Second, you check the model. Because if you are touching the model, again, it has to go through the approval process. That is the problem with models. Models will be implemented upon getting the approvals from the people are going to use it and all, everybody should agree to it. And so model alterations are difficult to be done. And you only have option of playing with the data. And after making changes to the data, still the model is not performing well, then you have to go and change the model. I'm telling a simple example. Loan approval process. This time you got data of, let us say, self-employed people and less of salaried people. In your initial model, you built a model where more salaried people are there. Less people of self-employed professional, self-employed people were there in the original data. Now you got a new data where you have salaried employees less, self-employed sir. That means your model will have a problem. So you have to fine tune the data and check the data how much. See, salaried average, self-employed average, there will be always difference. Typically, salaried guys will get a higher average because their salary will be stable, constant and all. Self-employeds depend, right? Some months they might get higher income, some months they might get lower income. So the volatility or standard deviation will be very high for self-employed people. Whereas standard deviation for income people will be very, very less. Because their salary is fixed. Every month they'll get the same thing. Until unless their EMIs increase or something, they have taken new loans or something, there you might see some change of. So you have to look at that one. A small change in the data also will make your model problematic. So that is the job of the data scientist. You have to understand what data is flowing in, make sure the same data comes into the model on which you built it. So you have to tell the guys, see, this model is more focused on the salaried employees. So the inbuilt data which is coming into the model should be more towards salaried employees. And you should build a separate model for self-employed employees, self-employed people or professionals. So these sort of changes will happen. So sometimes what happens is minor changes also will create a lot of problems in the data. We have constantly seen this happening. So the job of the data scientist is, before you send the data to the models, you have to look at the new data, do the visualizations. All exploratory data analysis are done. Make sure it is similar, almost similar to the original data. If there are big deviations, then your existing model will not work. You have to immediately raise a flag and then you have to rework now before reworking the model, you have to make sure whether the new data pattern will be same in future, or is it a one thing? Is it a one-time change, or every time you will get a new data? That also you have to be very drastic changes happen in model performance if the data, minor changes in data will lead to drastic changes in the models. That is the problem. That is the reason why still data scientists are employed. Otherwise, AutoML will take care. Everything is automated. Database to data model, deployment, everything is automated in cloud. You put a time frame, it will on that day, it will extract the data, put it to the model, fully automated process. But still we need people, because any changes in the data will lead to changes in the model performance. So this is the difference between the three models. In decision tree, you will get only one single tree. The other two are multi-tree models. Gradient boosting is sequential. See, until tree 1 is completed, you cannot build tree 2. Until these two are over, you cannot build tree 3. Sequential, you can see the arrows, right? Whereas these are all parallel, because samples are independent, right? In random forest, sampling is independent. Each sample is independent. There is no relationship between one sample and the other sample. So that is why you parallelly build random forest decision trees. So this is the difference between decision tree, which is a single tree model. Gradient boosting is a sequential building model, and random forest is a parallel building model. The tree-based models, which are very good in data science, their performance is one of the best in data science. The problem with the gradient boosting and random forest is computing power. They require computing power. Now let us implement from sklearn dot ensemble gradient boosting regressor 99.94 GBM predict is equal to GBM model 3D dot data frame np dot exp GBM predict 2_CSV GBM dot CSV. See, 0.13393 1234 0.1393 best performance compared to all other. Who is submitted? Bharat is there. Bharat, no, right? Not. You submitted GBM. What is 1300? 0.13 random now, so it will be slightly different. Random, first is random. After that you change. Max depth range 516 to max depth range 5 to 16, difference of 2. Min sample splits range 200 to 1001 with range of 200. Number of estimate is 60, learning rate CV is equal to 5. And once you build these different parameter models, you will identify the best model. See, max depth 9, split 1000, you got 0.83. So this is all based on grid search models. We call it as parameters, hyperparameter tuning using grid search methods. So not only estimators, you can do a lot of other arguments are also there in GBM, which needs to be tuned. If you want to get a best, see, randomized search CV. You have to randomize search CV and you give these various options, then you might get an optimal value of hyperparameter tuning. But that is also not guaranteed that it will work. So it all depends on the data, and you have to choose the trees based on the. So here he is trying different types of learning rates. So you can use this many, or let us try one method so that you can understand. Indentation error. Line 6, it is saying error. So error is pointing to accuracy. He got an output, but he got it only. So you got the predictions for each tree. So how will we get? So you can see here for different trees, this is how we do grid search. I have given 100, 200, 300, 400, 500 trees and R square for each tree, we are getting it. This is how grid search will work. So R square for each model, not predicting, for scoring of each model, you'll get it. Try adding RMSE to this. Now we are getting it correctly. So as we increase the trees, we get the reduced RMSE, right? Rest of you guys got it? Similarly, you can do it for random forest. So based on this, which trees have the lowest RMSE? 3959. Lowest RMSE is 3959. So we have to give 1000 trees as our model estimate.
ये सब वो करने का जरूरत नहीं है वहाँ आज तुझे कुछ भेजो कल तुझे रैंडम फॉरेस्ट और इसका भेजूंगा पूरा थोड़ा उसमें मतलब अननेसेसरी इंफॉर्मेशन दी है ओवर तो पहले भेज
So you can also do the same thing for random forest. Just change the name. Boosting weak learners. No, GBM will be the best model. GBM will be the best model. See, the RMS is not reducing. No, in GBM you got lowest RMS of 3959. Here it is stuck. It is still at 10,000 only. It is not going beyond 10,762. This itself tells us that this is not a better fit model. Whereas in case of GBM, we got 3959, right? Which is the lowest RMSE. In fact, if you run all regressor models, that would be the best option. GBM will be the best option.